Okay, gang, so the last thing we'll cover today is going to be the three types of chemical bonds that we're going to use in biology, um, and that we'll talk about at other points during the year when we start talking about bonds and how they're important with the science that we're going to cover. So the three types for us, there's more than three, but for the three types for us, it's going to be the covalent bond when electrons are shared. An example would be like oxygen, like we call that dioxide, which is atmospheric oxygen. Ionic bonds, where electrons are taken and they're not shared. We already had an example of that. It's going to be salt. And then we're talking about hydrogen bonds, which is not really a bond at all. It's actually just a weak attraction between hydrogen, usually a slightly positive hydrogen atom, and a slightly negative atom on a different molecule. And it's actually one of the keystones of life is the hydrogen bond. So it's really important that we kind of understand. And our example for that we'll use is water. You can imagine water is kind of important. You're 75% water, and water is the median in which all our chemistry happens, our biology happens in water. So you can imagine water is going to be important. So that hydrogen bond especially is going to be important. So looking at covalent bonds first. Again, this is a bond where electrons are shared between two atoms. We'll use dioxide, atmospheric oxygen, as our example. And you can see here's an oxygen. Oxygen is an atomic number of 8, and that means it has 8 protons and 8 electrons, right? So 2 in the first shell, and then 6 in its outer. But it's only missing 2, so it's pretty electronegative. It's going to want to take electrons and fill up that outer shell so it feels like it has a full outer shell. Well, another oxygen in this, right next to it feels the same way. It needs 2 more to have a full outer shell. So what happens, they end up binding together and they share their electrons. So what happens is, let's do this. Let's count the number of electrons that are green. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8. But how many are within the outer orbital? Well, it'd be those 8 plus these 2 purple ones. So this oxygen kind of feels like it has 2 more. This oxygen, if you count them up, all the purple ones, 1, 2, 3, 4, 5, 6, 7, 8, awesome. But within its orbit, it has 10. It's got these 2 green ones, right? So it also feels like it has a full outer shell. If I were to actually draw how these extra electrons orbited, it would be a figure 8. It would go around both of them. Each atom is going to share the electrons with the other atom for the purpose of kind of getting their fix, getting feeling like they have 2 more electrons in their outer shell. And by doing so, they bond together. And we call this a covalent bond because they cooperate and they share. And that's really important. This is actually a really strong bond. A lot of the bonds that we see within organic chemistry are all covalent bonds. So that's a really kind of important one. But again, in this case, the atoms are being shared. They spend time around both, the electrons are being shared around both atoms. Ionic bonds, which we've kind of covered before, right? Bond where one atom takes the electron from another atom. It's not being shared. That electron's only going to stay with that one atom. It's never going to go to the other. But we get the forming of ions, right? So we get a positive sodium, a negative chlorine. They stick together and form NaCl. If you don't remember, go back and look at the notes that we covered on what an ion is, because we also covered ionic bonds there. The little illustration kind of shows how that happens. Let's say sodium loses its one outer, chlorine gains the one it needs, and they both get a charge, and now they stick together like magnets. So the last type of bond we'll cover is hydrogen bonds. Again, hydrogen bonds is not really a bond at all. It's just a weak attraction between a slightly positive hydrogen atom and a slightly negative atom that's on another molecule. Not on the same molecule, it has to be on another molecule. These are very easily broken because they are so weak, and that's going to be important. The example that we use is dihydrogen oxide, which is also known as water. In its liquid form, here's a water molecule, H2 and an O. Here's another one, H2 and an O. So what's happening is that the electrons that oxygen needs is around the hydrogen. Hydrogen only has one. It's not going to just give it up. So a covalent bond forms where oxygen kind of gets the electron from these 2 hydrogens, makes them slightly negative. The hydrogens are slightly losing that electron, which makes them slightly positive. So Water is what we call a polar molecule. We'll discuss that more in the next unit, but it means it has a positive side and it has a negative side. So it's like a little magnet. So this positive hydrogen is going to be attracted to the negative oxygen on another water molecule, but it's not a bond, it's just a weak attraction. Liquid water makes and breaks these bonds, billions of times per second, and even just a droplet of water, because they're constantly wanting to stay next to each other. How do we know that that's what's going on? Well, water is pretty sticky, right? You can stick your finger in it and pull it out. There's water stuck to you. You want to clean up some salt and sugar that you spilled, spray water on a paper towel, then wipe it up. It will stick to it because water's like little magnets, and it's that hydrogen bond that is actually causing them to stick together. How do we know this is easily broken? Well, can you push your hand into water? Yes, you can. You're splitting the hydrogen bonds, and some water molecules are going to one side, other ones are separating and going to the other side of your hand. Can you push your hand into a block of salt? No, you can't. So an ionic bond is pretty hard to break. So an easy kind of way to tell these are actually weak bonds. There's a molecule in your body called DNA. You've heard of it before, and most of us know that DNA is double-stranded, right? It's got a strand running up, a strand running down, but it's two sides. But in order to read DNA, to copy it, or to read the code that's on the inside, enzymes have to separate the two strands from each other. They have to separate bonds. Which type of bond do you think DNA uses to hold the two strands together? Well, it's not going to be a covalent or ionic. That's too hard to break. They use hydrogen bonds to hold your DNA together. So it's easy to split that weak attraction and open up your DNA. So there's some cool properties that water has because of this. Hydrogen does this whenever it bonds to things, different molecules, like in your DNA and RNA. So that's an important type of bond that we use not only in chemistry but in biology as well. So I hope this has been informative. I hope you've learned something from it, and I wish you the best of luck. If you got any comments or questions, come by and see me, shoot me an email, give me a phone call, leave a message, and I hope to see you guys again in the future. Have a great day.